Welcome to this tutorial class on fluid machines. Today I will be solving two problems on the centrifugal pumps. The first will be a basic problem on the concept of centrifugal pump, and the second problem will be based on cavitation. So, let us start with the first problem. Let me read it out. The impeller of a centrifugal pump is 0.5 meter in diameter and it rotates at 1200 rpm. The blades are curved back to an angle of 30 degree to the tangent at the outlet tip. If the measured velocity of flow at the outlet is 5 meter per second, then we have to find out the work input per kg of water per second. We have to also find out the theoretical maximum height to which the water can be raised if the pump is provided with a whirlpool chamber which reduces the velocity at outlet by 50%. So, before starting the problem, let me discuss about the velocity diagrams. So, as you can see, these are the impeller blades and this is the inlet velocity diagram, and for a pump in general we assume, and in practical also it is seen that the flow actually enters radially. So, we will be assuming the flow to enter radially at the inlet, that is we will be considering VW1 or the tangential velocity at inlet to be 0. So, this is actually the peripheral velocity of impeller blade at the inlet, this is the radial velocity at inlet, and this is the absolute velocity at inlet. This angle is the impeller blade angle at the inlet made with the tangent drawn at the bottom of the impeller blade, that is this is designated by beta 1. Next, moving on to the outlet velocity diagram. Here you can see that this is the relative velocity at outlet, this is the peripheral velocity of the impeller blade at the outlet, this is the absolute velocity of at the outlet of the impeller, this is the flow velocity. This angle which is made by the impeller blade at the outlet with the tangent drawn at the tip is the blade angle of the impeller at the outlet and is designated by beta 2, and the tangential component of the velocity at the outlet, that is VW2, is given by this portion, that is VW2. So, moving back to the problem. So, let us write down what the parameters that are given. So, we are given the diameter of the impeller for the centrifugal pump as 0.5 meters. The rotational velocity is given as 1200 rpm. The angle beta 2, as we discussed, is given as 30 degree. So, this angle is given as 30 degree. Next, we are given the velocity of flow at the outlets, that is Vf2 is given as 5 meter per second. So, we have to find out the work input per kg per second, then that is actually given by, that is we have to find out this work. Okay, so, the expression for work done, work input per kg of water per second is actually given by this expression VWT U2 minus U1 into VW1 by G. We know that VW1 is 0. So, what we are left with is VW2 into U2 by G. Now, U2 is obtained, which is the peripheral velocity of impeller blade at the outlet, from this expression. We know both the values of N and D. So, substituting them, we get the value of u2 as 31.4 meter per second. Vw2 on the other hand can be obtained from the velocity diagram, that is this portion. As you can see from this diagram, Vw2 is given as u2 minus of this portion, which is Vf2 cot of beta 2. So, substituting the values, we know the value of u2, Vf2, that is the flow velocity at the outlet, as given as 5 meter per second. So, and beta 2 is 30 degree. So, if you substitute the values, we get the value of Vw2 as 22.74. So, substituting the value of Vw2 and u2 here, we ultimately get the work done per kg of water, per unit weight of water as 72.78 meters. Next, we are required to find the maximum height which the water can be raised if the pump is provided with a whirlpool chamber which reduces the outlet absolute velocity by 50%. That is, for the second part, we have said that the outlet velocity is reduced by 50%. So, actually the loss in absolute velocity at the outlet is 0.5 into V2. So, the corresponding loss in velocity head at outlet is 0.5 into V2 whole square by 2g. Now, we can write that the total head that is developed by the pump is equal to the total work input. That is, in the ideal case, we can write that the total head developed by the pump is equal to the total work input given, or total work input per unit weight of water. This quantity we just found out, which was 72.78 meters. So, the total head in the ideal case we can say is actually 72.78 meters, but there was a loss in velocity head which amounts to 0.5 into V2 whole square by 2g. So, the net head available, or the maximum, or the net head which, or the height to which the water can be raised is, that is the maximum height to which the water can be raised is actually h minus two into g. So, that is the net head developed is actually the maximum height to which the water can be raised. Now, the unknown here is V2, that is the absolute velocity at the outlet. So, we again refer to the velocity diagram at the outlet, and we can see from this velocity triangle, that V2 is equal to, or rather V2 square is equal to Vw square, Vw2 square plus Vf2 square. We know the value of Vw2 and Vf2 is given in the problem as 5 meters. So, substituting those values, we ultimately get the value of V2 as 23.38 meter per second. So, we substitute the value of V2 in this expression, we know the value of h. So, the height that we are required to find out comes out as 65.87 meters. So, this is the end of problem 1. Now, let us move on to the next problem regarding cavitation. Let me read out the problem. During a laboratory test on a pump, appreciable cavitation began when the pressure plus the velocity head at the inlet was, that is the pressure plus the velocity head at the inlet was reduced to 3.26 meters, while the total change in head across the pump was 36.5 meters and the discharge was 48 liters per second. The barometric pressure was 750 millimeter of mercury, that is the atmospheric pressure was 750 millimeter of mercury, and the vapor pressure of water is 1.8 kilopascal. So, we have to find the value of sigma c, which is actually the critical cavitation factor, critical cavitation parameter. Next, we have to find if the pump is to give the same total head and discharge in a location where the normal atmospheric pressure is 622 millimeter of Hg and the vapor pressure of water is 830 pascal, by how much must the height of the pump at the supply level be reduced. So, before starting the problem, let me show you a schematic of the pump. So, as you can see here, this is the water level in the reservoir. We denote it by A, this section, and we will consider this as the datum. This is the impeller inlet. This section we denote as 1, and this elevation or the height between the impeller inlet and the reservoir water level is denoted by Z. So, all the parameters, all the variables which denote the which is at the inlet of the impeller are denoted by subscript 1, and the parameters or the variables at the reservoir water level are denoted by subscript A. So, let us write down the parameters that are given. First, we are given that the pressure plus the pressure head at the impeller inlet plus the velocity head at the impeller inlet, the sum of those two is equal to 3.26 for cavitation to begin. So, for the cavitation to take place, this should be the total head or the sum of the pressure head and the velocity head at the impeller inlet for cavitation to start. Next, we are given the net head change across the pump as is 36.5 meters. The discharge is given as 48 liters per second, which is 0.048 meter cube per second. The atmospheric pressure is given as, and we note that this, since this is exposed to the atmosphere, so the pressure head or the pressure at this section is actually the atmospheric pressure itself. Another point to note is that this at the reservoir water level, at the reservoir the water is almost stationary. So, the velocity head at this portion is also 0. So, the atmospheric pressure is given as 750 millimeter of mercury, or actually this is the atmospheric pressure head, which can be written as 750 into 13.6 divided by 1000 meter of water. So, this comes out as okay. Let us leave it like this only. Next, the vapor pressure at this temperature and pressure at this atmospheric temperature pressure and temperature is given as 1800 Pascal. So, we are required to find out the value of sigma c, which is the critical cavitation parameter. And it is given as the pressure head at the reservoir water surface minus, that is the atmospheric pressure, minus the pressure head at the impeller inlet minus the elevation, that is the elevation between the impeller inlet and the reservoir, minus the head loss due to friction in the pipe connecting the reservoir and the impeller inlet, that is Hf is the frictional head loss, and divided by total head. So, we are required to find out this quantity. In the second part, we will be discussing that later. So, first let us deal with the first part. So, for cavitation to take place, the inlet pressure at the impeller is equal to the vapor pressure, that is 1800 Pascal. So, the inlet pressure head at the impeller is which comes out as 0.183 meters. Next, since we are given the sum of the pressure and the velocity head at the inlet, so from this we can get the velocity head at the inlet by subtracting the pressure head which we just obtained. So, the velocity head at the impeller inlet is obtained as minus the pressure head at inlet, which is 3.08 meters. Now, let us apply the Bernoulli's equation between this section and the impeller inlet. So, if we apply the Bernoulli's equation, we get Bernoulli's equation P A by rho g, that is the pressure head at the reservoir plus the velocity head at the reservoir, plus, since this is the data, the height elevation is 0, this is also 0 as we already talked about, that is the velocity at the reservoir level is 0. Next, the is equal to the pressure head at the reservoir inlet, pressure head at the impeller inlet, the velocity head at the impeller inlet, it is, this will be 2 V 1 square plus 2 g, V 1 square by 2 g plus the elevation, that is z, plus the head loss. So, from here we can write P A by rho g minus P 1 by rho g minus of z minus H f is equal to V 1 square by 2 g. Also, from here we can write z plus H f is equal to P A by rho g minus P 1 by rho g plus V 1 square by 2 g. So, this we know as 3.26, which was given in the problem. 3.26, and this 2 is given in the problem. Pa by rho g, this was given in the problem. So, substituting the values here, we get this value of the potential head plus the head loss at the impeller inlet as 6.93 meters. Now, if we can recall, the expression for the critical cavitation parameter was this. So, we just derived that this expression is nothing but the velocity head at the impeller inlet. So, from here we can write sigma c is V1 square by 2g whole divided by h. So, we know the value of h, and V1 square by that is the velocity head at the inlet to the impeller, we have already found out as 3.08 meters. So, substituting the values, the head was given as 36.5 meters. So, sigma c comes out to be 0.084. Now, let us move on to the next part. In the next part, the atmospheric pressure was given as 622 millimeter of Hg, that is atmospheric pressure head is 622 into 13.6 divided by 1000 meter of water, and the vapor pressure of water in this case was given as, which is also equal to the pressure at the inlet to the impeller, 830 Pascal. So, we have to find out by how much the height of the pump at above the supply level should be reduced. So, let us find out the elevation for this case. So, we again apply the Bernoulli's equation, just like in the previous case. So, for the reservoir, we have only Pa by rho g, that is the pressure head, equal to P1 by rho g plus V1 square by 2g plus z. Let us denote this z by z1 plus hf. Now, it is given here that the head remains the same and also the discharge remains the same. So, since the discharge is the same as in the previous case, this signifies that the velocity is also the same, or in other words, the velocity head at the inlet, at the impeller inlet, remains the same. That is, it is still V1 square by 2g. This is because the discharge remains the same. So, also since the pump is the same as in the previous case, so the head loss due to friction in the pipe connecting the impeller inlet and the reservoir is also the same. So, Hf is also the same as in the previous case. So, we have the head as well as the discharge and also the velocity head at the inlet of the impeller same. So, from here we find out Z1 plus Hf, which is Pa by rho g minus of P1 by rho g plus, where rho is the density of water, minus of V1 square by 2g. This is the same as in the previous case. This is 830 divided by 9.81 into 1000, and this we have already found out, which is 622 into 13.6 by 1000. So, we V1 square by 2g in the previous case we found out as 3.08 meter. So, we substitute these values, that is this is 3.08 meter. Substituting these values, we get the value of Z1 plus HF as 5.29 meters. So, the height of the pump should be reduced that is above the pump height of the pump above the supply level or above the reservoir water level should be reduced by the height, that is Z plus HF minus of Z1 plus HF. Now, that is the height that H is equal to required height is Z minus or Z1, since HF is the same. This cancels out. Now, we have found out Z plus HF in the initial Z plus HF as 6.93, that is 6.3 minus of Z1 plus HF we just found out as 5.29 meter. This is actually the difference of Z plus HF minus of Z1 plus HF. So, this comes out as 1.64 meters. So, this is the required height. With this I end this second problem. So, this ends today's lecture. Thank you.